We earlier discussed direct mapped caches, and the disadvantage with a direct mapped cache is, for example, if you have a cache with 8 lines, and then you have an address which has an index 000, it is going to go into exactly one place in the cache. It cannot go into any other place in the cache. And now, if you get the next address to be 10000 with the same index, it's going to go and evict this already existing line. It is going to replace that line in the cache. So now next, let's say you get 000 again, then it is going to go and evict this previous block. And then next again, if you get 100, it is going to evict the previous block and so on. So you're going to always keep getting cache misses. And that is the reason why direct mapped caches are not preferred. So we want to have more flexible placement of cache blocks. So now consider this cache, which is a direct mapped cache, and we know that the data can be placed in only one block in the cache. Now let us say we split this up into two halves, which means we reduce the number of lines in the cache, and then we take this block and then put it in the next column of the cache. So this kind of a cache wherein there is there are lesser number of rows, and the rows are now called set, and the same set, the concept of a set is the same as the line here, and you index it into the set using the same index bits and so on. I'll explain about it later. So basically you have a certain number of rows, which is also called a set, and then a single set is going to have multiple tag data columns. So you can think of this as one direct mapped cache and this as another direct mapped cache, but they're sharing the same index. So how this works, I'll explain. Now, this kind of a cache is called a set associative cache. The row is called a set and the columns are called ways, because there are uh, two columns, that is two tag data columns. It is called two-way set associative cache. Now, similarly, you can have a four-way set associative cache, which is a four tag data columns. The number of rows can be anything. Here it is just shown as two, but it can be anything. But lastly, the other type is you have just a single uh, row or a single set, and you have multiple columns, that is multiple tag data columns. So this kind of a cache is, you can either call it eight-way set associative because there are 8 columns, or it is called fully associative. It's called fully associative because there are no multiple rows, there's a single row. So these are the different types of caches we have. Now we will see how it works. So you can think of the set associative cache as a parking space analogy. You can compare it with that. So what you can do is you can have, let's say you have a lot of parking spaces, you're going to divide them into multiple sets and then each having certain number of spaces. So for example, instead of telling you to park your car only in this particular block, let us say you're given this entire uh, block, or what we call way in the cache, and you're given a certain row, and you are free to place your car anywhere in this particular uh, particular row. So this is the first way, this is the second way, and so on. So you can place it in any particular column of that particular row. So some kind of a flexible placement of blocks is what set associative gives us. Let's see how this works. Firstly, let us get familiarized with the terminology. Each row is called a set, each column is called a way, and each way has a tag and a data. Now remember that there is only one index. There's one common index for all of these, and each data has its own has a tag associated with it, which means each of it has a separate tag associated with it, like you can see here. So you can think of them as four parallel direct mapped caches. So you can think of it that way. Now, how do you place the data in the cache? Now, let us say we get a certain address, a 32-bit address. Let us consider this 32-bit address. And clearly you have four ways here. And there are number of rows or number of lines, or actually the set size is 256 entries. There are 256 rows in this cache. So how many index bits do you have? Because there are 256 rows or sets, you have um, 8 index bits, because 2 power 8 is 256. So index bits is 8. Also, we want to make it byte addressable. So because we want to make it byte addressable, and we are saying that, let us say each of this is 32 bits of data as shown here, which is 4 bytes. So in order to address each byte, you need 2 bits, and therefore the least 2 bits of the address will go for the byte offset. The next 8 bits is going to go for the index, and the remaining is going to go for the tag. So this is the same way you used to index into the direct mapped cache. Now what is the difference here is, let us take a simple example. Now let us say you get an index 0, an address with an index 0, which is 8 zeros, because our index is 8 bits. So that particular data is going to go here into the first way, which is free, and you update its tag and the valid bit. Now the tag could be anything else. Let's say it is something like this. Now let's say you get another address with the same index. Now what was happening earlier with the direct map cache was there was only one column in the direct map cache. So you had to evict this particular line, and then you had to replace that with the new data. Now, you don't have to do that in a set associative cache. What you can simply do is you take this data, which is coming from this particular address. It has a different tag. That is why it is a cache miss, right? If it was the same tag, then you would say it is a cache hit, because it's already present in the first way. But because you get a different address with a different tag, instead of, you don't have to evict this line, what you can do is you can simply place it in the next way. You can place the new data in this way, and you update its tag and the valid bit. Now let's say you get another address with a different tag but the same index. So if you get a new tag, a new data with a different tag and the same index, you would index into the same row. The first thing is you would try to match the tags. The tags are different, so it's a cache miss. And therefore, you want to now bring in this data from the memory. So you also see that these two ways are empty, and therefore you would place the new data in this column, which is free, update its tag and valid, and so on. So now let's say the fourth one is also occupied. Okay, so this way you don't have to evict the previously existing data, but you can fill up to 4 ways. Now what will happen when you get the same index for the fifth time? Let us say you get a new data with this kind of the same index, but a different tag. The tag does not match with any of these, so it's a cache miss. Therefore, you have to bring in new data. So now when you bring in new data, it has to go into this particular row. There is, because it matches the index. Now, you definitely know that you have to evict one of these or remove one of these data, because you have to now bring in new data. Now, which one will you evict? So that is the problem of uh, replacement algorithms. So there are several replacement algorithms to replace or evict data in a set associative cache. In a direct mapped cache, you have no problem because there is only one data that you can evict. Whereas in a set associative, there are 4 ways and you can evict any of those. So it completely depends on the algorithm that you want to choose. So this is the way um you work with set associative caches. Now let us consider the case where, uh, let us go back to this slide because it is easier. Let us say we have data in all of these uh, all of these ways or blocks. And now you get a new uh, let's say you get a new address. So the index bits is 3 because the number of rows is 8. And let us say you have some tag bits. So how do you compare all of these tags? So let us remember and recall that the way you work with caches is, first thing is you separate the data, separate the address into index and tag bits. You go to that particular index and then you compare the tag. Now there are 4 tags here because there are 4 ways. So which one would you compare? You will have to compare with all of them, and you do that parallelly. So compare all of the tags from the ways in parallel to check if they match. And they're going to match with exactly one tag, not with multiple tags. I hope you understand that. So let us say it matches with this tag, then it means that it's a cache hit in the first way, and you're going to pull in the data from this particular way. So that is how you do a tag match with all the ways in parallel. So let us look at one example. You have a 4-way set associative cache and you have 64 kilobytes of data. Each block contains 32 bytes. The address is 32 bits wide. Now you have to answer how many sets are there and what are the sizes of the tag, index, block offset fields, and so on. So how do you work with this? There are 64, this is 64 kilobytes of data, and each block is 32 bytes. So since each block is 32 bytes, so what is a block? You had a tag and a data, and you had another tag and a data. So this is, each of this is a way. So now each of this is 32 bytes. So that's what it says. So this is 32 bytes of data. So how many, if you need to do byte addressing, you need 5 bits to address it. So that's the first easiest thing to do. You need 5 bits for the block offset or the byte offset. So the next thing is you've been given the size of the cache is 64 kilobytes. So you can divide the 64 kilobytes by this 32 blocks, and you will get to know how many blocks are there in the cache. Now, you have also been told that it's a 4-way set associative cache, which means that there are 4 columns here. This is tag data. So you have overall, now you know there are 2048 blocks, but you want to know how many rows are there. You don't know how many rows are there. So, but you know how many columns are there. There are 4 columns because it's a 4-way cache. So if you simply divide 2048 by 4, you are going to get the number of rows or number of sets in the cache. Once you know the number of sets in the cache, you can figure out the number of index bits. And if you subtract the overall number of address bits minus the byte offset minus the index, you're going to get the tag bits.